Alright friends, welcome back. In this video I'd like to go ahead and take a look at section 2.3 of your textbook, and that talks all about how to analyze graphs of functions. So in this video I want to talk about a different couple of characteristics of functions. I want to talk about domain and range. I want to talk about how you can evaluate the function using the graph. I want to talk about some other things about like zeros and talking about even and odd. So lots of different things dealing with the graphs of functions today in this video. So first of all, talking about domain and range. So the idea with domain, of course, is that it's all of the x values that your function can assume. So if I really quickly take a look here at this function f of x, what I might do really quick is go through on the x-axis and put a couple of points or dots on each one of these x values here. And the idea is, what I want to do is I want to see which one of these can be dragged up or down to touch the graph, okay? And so pretty obviously, I think if you were to begin starting to do that, we could do this one, and this one, and this one. These are all ones that you could drag down to touch the graph. This one here, we could drag these ones up to touch the graph, so that's pretty good. And then continue to go through, and what you'll notice here is once we get to this one here, if we drag this one down to try to touch the graph here, it's going to miss completely. It's going to go right through that hole and miss the graph. Okay, so what that's going to mean is that this is an x value that we have to exclude from our domain. We're only interested in the ones that we can drag down to touch the graph, and then pretty obviously I think you'll be able to tell here that we would not be able to hit there, and we would not be able to hit there as well. We miss the graph completely when we try to drag those down. So that's going to mean that these are not in our domain. However, if you were to take a look at all of these x values here and draw them down to the graph, they would touch. So what we want to do is we want to go ahead and convey the idea that we want everything up to this value, but not including that value. So I'll use a little bit of a parenthesis there to help me remember that. And then on the left side of things here, again, same thing. If I try to drag this point down, I'm going to miss the graph completely, so I'm going to have to exclude that from my domain here as well. Now, if I were to take a look at this region of x values that touch my graph, it looks like I'm going to have the region that begins here at this x value and then goes all the way through until I reach this little boundary right here. And so what we would want to do is go ahead and describe that region using our interval notation. So it looks like that is the region that is going to start here at -6 and then go all the way until we reach up to +4, but not including +4. So matter of fact, let me try to recount that again. I think that is actually not -6. That's going to be -5. There we go. My apologies. So we want to go ahead and make that correction and then write our interval down here in our domain for f of x. So I would say the interval from -5, including -5, all the way up to +4 with a parenthesis around that. Okay, so it's as easy as that. If I wanted to go through and do my range now, I could by doing the exact same process. I can think about this in the exact same way, maybe going ahead and not taking a look at those values on the x-axis, but instead here taking a look at these values here on the y-axis. Okay, if I were to go ahead and take a look at these are all ones that I believe can touch the graph if we were to go ahead and drag them to the left or to the right. Okay, so if I were to start up at the top, it's already touching the graph. I could drag this one to the left or to the right here. To the left or to the right, we would be touching. To the left or to the right, exactly the same thing as we go all the way down through every single one of these. But when we reach down here to this last value here, this would be something that I would want to drag to the right, and you'll notice that I miss the graph completely. So that is going to have to be a y value that we exclude from our range whenever we get to talking about that. And then obviously if we continue to go up here on the y-axis, all of these y values here, these would all miss that graph of f of x completely. We're going to take a look at the graph of g of x here in a moment. But these would be ones that we would exclude from our range here as well. And so if we go ahead and take a look at that, that would be the region of y values that lives in this range right here. Okay, and so we would want to go ahead and describe that region by using interval notation again. So it looks like down here, this is the value of -6, and up here, this is a value of 1. And so our range would be in that region there. So I would say the region from -6, not including -6, because remember at that point down here, -6, I actually would have to go ahead and continue my little region there, right? Because then all these little values here would be dragged over to touch the graph here as well. So I would say from -6 all the way to +1 and then close that set off. Okay, I go ahead and encourage you to maybe pause the video and see if you could try G yourself. I'm not going to go ahead and talk through it, but I will go ahead and share with you that the correct responses that you should have there. Again, try to pause the video and see if you could do this yourself, but the domain for that would be -∞ to 5 and then 1 to +∞, because those regions will just keep going indefinitely to the left or to the right. Okay, so let's go ahead and move on here and use the graph to evaluate, right? So if we have the function plotted, we can actually go ahead and use the shape to evaluate functions, remembering that the notation says that this number that I have here inside the parentheses, this is the input, and what we want to go ahead and do is figure out what the output would be. Well, just keep in mind that points that are on the graph are going to have those as coordinates. It's going to be your input as the x-coordinate and the output as the y-coordinate. Okay, so what we're going to have to do is just check and see if we could go ahead and find positive 4 there as our input, or on the x-axis. We just need to find the corresponding y value to that. So if I go to positive 4 here, which I want to switch to my pen there, so there we go. If I go to positive 4 here, and I follow this graph all the way up until I touch the graph right there, what I want to do is I want to figure out what the corresponding y value would be there, and that, of course, would be the output that we would have. Now, that looks like would be an output of positive 3, so that's going to mean for us that the f of 4 is going to equal positive 3, okay? Likewise, again, we would just do all these in the exact same way, so if we were to look at 2, that's right here. If we follow that all the way up, it would touch the graph right here. And if we go over to the y-axis, that looks like that would be a y value of 4. So that means that whenever the input is 2, the output is 4. I would encourage you to go ahead and pause the video now and take a look at these other inputs here and figure out what the corresponding outputs would be. And then let me go ahead and just write these in here. Hopefully you've had a chance to pause the video, but here I'm just going to go ahead and say negative 3, 1, and 0 is what you would find there. Now, graphically speaking, we want to make sure that the graph that we're looking at is the graph of a function, okay? So there's a lot of results that are going to come down the pipeline for us in later chapters that are going to be handy tools in our toolbox, but we have to make sure that we're working with a function first. So it's important that we know how to figure out if a graph is a function. And so we have this vertical line test to determine if it's a function or not. So very simply stated, it says right here, if every vertical line intersects the graph once, and only once, then the graph is a function. Okay, so you can see some examples over here. If you look at that yellow graph of y is equal to f of x, this would be something that would be a function, because no matter where you put this vertical dotted line, it's only going to intersect that shape in one place and not in 2 places at once. This blue graph over here of y is equal to g of x, not the case for that, because you can see there with one vertical line, I can set it up to where I'm actually touching the graph of that in 3 different places, and that would mean that I would have an x value that corresponds to 3 different y values there, and we obviously don't want that. So as far as answering these questions over here off to the side, is f of x a function? Yes, that was our yellow one. Is g of x a function? No, that was our blue one. It does not pass the vertical line test. So really easy test to see if a function is in fact a function when it's graphed. Talking about the zeros of functions, the reason that we are interested in these is because zeros tell us exactly where our x-intercepts live on our graph, okay? Very handy to be able to analyze the graph when you know where the graph crosses the x-axis. So it's important that we know how to find our zeros. And this is more of an algebraic thing than a graph thing, but all the zeros are the solutions to the equation your function output equals 0, okay? And so if I give you an example here where I ask you to find the zeros of this function, here is the function output. It just says f of x is equal to 3 times x squared plus x minus 10 all over 4x. What I'm interested in is the zeros. So what I'm interested in is where does f of x equal 0, okay? So what I'm going to do to solve this algebraically, and my goodness, that is a very thick pen tip, so let me change that. What I'm interested in is where does f of x equals 0. So what I'm going to do is I'm going to substitute in 0 for f of x, and I'm going to go ahead and continue to solve this equation here. So if I do that, recall that on the right-hand side, this is something that we used to call a rational expression because it's a polynomial over a polynomial, and a rational expression is equal to 0 exactly where its numerator is equal to 0. So for that reason, I'm just going to go ahead and set the numerator equal to 0. I'm going to go ahead and solve this. Now, that's just a simple quadratic equation, and that's not something I'm really going to take a lot of time to talk about how to solve here. I would expect that you guys could likely go ahead and do that on your own, but this would be the factorization of that polynomial, and again, just zero product property, we can get our zeros pretty quickly in this way. So x is equal to 5 over 3, and x is also equal to negative 2. So these are the zeros, but remember, the reason that we like to find these is because these correspond to points that are actually on the graph. Wherever you have a 0, that is going to be an x-intercept. So the coordinates of that x-intercept would be 5 over 3, 0, and the coordinates of this other one would be negative 2, 0. So it's basically whatever your 0 is, that is the x-coordinate, and then since these are x-intercepts, the y-coordinates are just always going to be 0. Moving right along here, some other examples where we're finding zeros. So same process, we still want to find the zeros of these functions here. So what I'm going to do is I'm going to go ahead and substitute 0 in the place of f of x, and then I'm going to go ahead and solve the equation to get x isolated here. So if I go ahead and add 2 to both sides here, add 2 to both sides, there we go, I wanted to do it in a different color, that would be 0 plus 2 is equal to the square root of 3x. To get rid of that square root, I will go ahead and apply an exponent of 2 to both sides of the equation, and that gets rid of that square root. So 2 is equal to, oh, sorry, not 2, we want 2 squared, right? So that would be 4. And then the square root goes away because we applied the exponent of 2. And then what we need to do after that is just simply divide everything by 3, and then x is by itself, and apparently that is going to be equal to a 4 over 3, okay? And so that is the only 0 of this graph, and just remember that that corresponds to a point on the actual graph, which has coordinates 4 over 3, 0. On this next one, we have a 4-term polynomial. We would want to go ahead and set this equal to 0 and solve. And again, the way that we would want to solve this is by factoring it and then using zero product property. And so since we have a 4-term polynomial, remember that we always factor these by grouping here. So I'd factor out a GCF in that first group of 4x squared. That's going to leave behind x minus 6. And recall that the leftovers for my second group need to be identical to those of the first group, so I could factor those out as a GCF here in the next line. So if I look at my second group, I can factor out a -1 in order to get that done. And then what I see here is 2 groups, and they both have an x minus 6 in common, so I can factor that out front. And that leaves behind, of course, 4x squared minus 1. And keep in mind, this is all equal to 0. Now, we have one step of our factorization done, but what you'll notice is that the 4x squared minus 1 is an example of the difference of 2 squares. And so I'm going to continue to factor that. X minus 6 times 2x plus 1 times 2x minus 1. Okay? And now I've split this up into the product of a bunch of linear factors here, and now I can go ahead and apply zero product property. X here would be equal to 6, x here would be equal to -1/2, and x here would be equal to +1/2. So these are all 3 zeros of this function. And again, keep in mind that these all correspond to x-intercepts on the graph. So that would be an example of a function that crosses the x-axis 3 times in those 3 places. Another characteristic about graphs that we're interested in is where our graph is increasing, decreasing, or constant. So the way that I always kind of like to explain this visually is picture that you are on a roller coaster, okay? So if the path of your graph was an actual roller coaster, then anywhere that you would be on your roller coaster where you start from a high point and then you ride the roller coaster down when it goes real fast, those are the exciting moments, those would be decreasing intervals, okay? So anytime that you are sloping down or falling on the roller coaster, that would be a decreasing interval, okay? Anywhere on the roller coaster where you would just be riding on flat ground, that would be a constant interval because the output will remain constant throughout that region. And then, of course, anywhere that you are going to be climbing, remember on those roller coasters, there's oftentimes that slow anticipation to reach all the way high up, and then that's followed usually by a decreasing interval where you go real fast. That's a lot of fun, right? So it's going to be on these intervals that we are going to be decreasing, constant, and increasing. And the way that we would describe these, of course, is by describing the x values that we are decreasing in, so or constant or increasing in. So if I look at the x values for that, my decreasing region starts here at an x value of -2, and we reach 0 until we stop decreasing. So this would be an interval on which I am decreasing from -2, which we'll say here. We are decreasing on that interval from -2 all the way to 0. And then after that, we would be constant from that interval from, it looks like 0 all the way until I reach +2. So that is a region on which I am constant, so from 0 to 2. And then finally, a region on which we are increasing would be from here at 2 all the way until we reach an x value of 4. That's where I stop increasing there. So we would go ahead and write that down here as the region from 2 to 4. That's where I'm increasing, okay? So again, I really like that, that roller coaster analogy. I think that makes it really easy to visually comprehend exactly where your regions would be that you are increasing, decreasing, or whatever, okay? So if we take a look at some more examples of that here, it looks like I have some increasing intervals here to start off with. I'm just going to go ahead and read this from left to right. So going to -infinity there, but then going all the way up, slow anticipation up to the very top, highest point you could be on a roller coaster, that would be a region on which we are increasing. So that would be a region here that would start from as far left as I can possibly be, which of course would be -infinity, all the way until we reach this x value, which it looks like is just simply -1 here. So it looks like I'm going to be increasing, which I'll do in the same color, from negative infinity all the way until I reach negative 1, that is going to be a region on which I am increasing in this graph, okay? And then after that, it looks like I am starting to decrease. So again, on the roller coaster, we have reached the very highest point you could be, and then we just start falling real fast until we reach this point right here. It looks like that interval is going to go from where we left off in our increasing interval, and it's going to come all the way until we reach, it looks like, an x value there of positive 4. And so what I would say here simply is that I am decreasing on this interval from negative 1 to positive 4. Okay, so decreasing from negative 1 to positive 4 there. And then after that, I pick up again with an increasing interval. So from that 4, that very lowest point that I could be, I would be climbing, and then my roller coaster ends and I can get off, right? So that would be the region that starts at 4 and reaches all the way until we reach this x value right here. It looks like that's kind of where my increasing interval stops, and that's going to be an x value of, it looks like, 1, 2, 3, 4, 5, 6, 7, 8. Sometimes you got to count it out, right? So up here on my list of increasing intervals, I just go ahead and maybe tack that on here. So maybe comma separator, I'm also increasing on that region from 4 to 8. Okay, so it looks like no constant regions there, but that's okay. Not all graphs have constant regions here. Taking a look at this next one, it looks like I am going to be increasing from as far left as I can be all the way until I reach this point, but not including that point. So that is going to be the region that is as far left as I can be all the way until I reach negative 5. So that would be an increasing interval from negative infinity all the way to negative 5. And then it looks like I am constant after that for a little bit. So from that point at negative 5, I am constant until I reach this x value here of, it looks like, positive 3. So that would be a region on which I stay constant. So I'll mark that. That's going to be the region from negative 5 to positive 3. That is where I'm constant. And then after that, we have our decreasing interval. Okay, so this would where we'd be falling on the roller coaster, and then that just kind of drifts off to infinity and beyond there. So we would go ahead and mark that as the rest of my real number line there. And so that value, of course, there is positive 3. So my decreasing interval would be from positive 3 all the way until I reach positive infinity there, okay? So what we're doing is we're taking a look at regions of the x-axis there and describing what we're doing. We are either increasing, constant, or we are decreasing. Okay. For this next couple of examples, it asks us an interesting question. It asks us, the functions are graphed here. It's asking us, where does the output become greater than or equal to 0? Okay. Well, keep in mind, the output f of x, that is on the y-axis here. Typically, we characterize that as y, but we always see here that y is equal to f of x. And so if we're interested where f of x is equal to or greater than 0, then that means, of course, we're interested in where y is greater than or equal to 0. Well, we know where y is equal to 0. That's just going to be right here at the origin. And then where are we greater than 0? Well, that's going to be for all of these y values that are on the positive region of your graph. So we basically do not want any of these negative regions at all. We are interested in only where does f of x become greater than or equal to 0. So in other words, non-negative, right? Well, it looks like on our graph we have, starting from the origin, it looks like we have this little snippet of the line right there, okay? And so if we're trying to point out where this function is greater than or equal to 0, we're going to go ahead and use the x values to describe that, okay? And so that would be what x values for that little snippet of the line there. Well, that would be an x value starting there where I begin of negative 2. And then what I would want to say is that since this is a line that just keeps reaching up indefinitely, then we would want to go ahead and point out the fact that all of these x values here, starting from where my line begins, but then reaching all the way as far right as I can go, these would be the x values on which my function is greater than or equal to 0. And so that would be from negative 2 all the way to positive infinity. That is where my function would be greater than or equal to 0. Over here with this function, again, where do we want to be greater than or equal to 0? Well, what you notice there on that part is that since your y is going to be 0 at the origin, we're basically only interested in the regions of these graphs that are above the x-axis, okay? So when we are being asked for this, that's an easy way to think about it, is we want the parts that are above the x-axis. So when I move on to this next graph here, where I have the parabola, then we have two parts that are above the x-axis. We have the part that starts here and swoops up to the left, and we have the part that starts here and swoops up to the right. So we are not interested at all in any of this part of the graph that lives below the x-axis because, again, we want our output to be non-negative. We want it to be greater than or equal to 0. And so on what x values does this occur? Well, again, we just have to kind of trace it back. Starting here, when we look at x values here, it looks like that's going to be from an x value of 0, but then reaching as far left as I can be, because remember, these parabolas have arrowheads at both ends. So that would be from negative infinity all the way until we reach an x value of 0. That would be one region. And then the other region is going to start over here at this other input, which is going to be 4. So that is going to be the region that begins at 4 and reaches all the way out to positive infinity. That is where we have this other part of the graph that only lives above the x-axis here. So these would be our solution sets for where that function is greater than or equal to 0. Moving right along here, getting into what it takes for a function to be even or odd. There's not a lot or too much here that I want to go ahead and point out, but I do want to kind of throw some things your way. Since we're talking about graphs in this video, we've already talked about in a past video how we can check algebraically to see if a function is even or odd, and those tests are just kind of summarized here above. But what I really want to hone in on here are these two guys right here, right? So the fact that if you have an even function, then you're going to have symmetry about the y-axis, okay? So very, very important stuff here. So as a quick example of that, an even function would be just your parent function for the quadratics. So something as simple as f of x is equal to x squared. Remember what that graph looks like. It just looks like your humble parabola there. Okay, this would be an even function, and what you'll notice is that this does have mirroring symmetry across the y-axis, right? I can go ahead and take any point that lives on this side and mirror it over to a corresponding point on the other side, and again, we are mirroring across the y-axis here, and so that would mean that I have y-axis symmetry on any even graph, okay? A dead giveaway that this would be an even function as well is that if you look at the exponent here, this is something that is an even number. All right, so especially if you have a polynomial function that you're graphing, look out for those even exponents, okay? For an odd function, this is going to be something that's not symmetric about one of the axes, but it will have rotational symmetry around the origin. So as a quick example of that, maybe something that looks like f of x is equal to x to the power of an odd number, like maybe say to the power of 3. If you remember what that function looks like from Algebra 2, swoops up like that, swoops down like that, okay? So again, this is not really something that we would say can be mirrored across one of the axes at all, but this will have some rotational symmetry. So if you were to go ahead and rotate this 180 degrees, then it would basically land on itself, okay? So that's what we mean whenever we say we have origin symmetry, is we're basically rotating with that origin point being the point that we're rotating around with. And again, a dead giveaway that this is going to be an odd function is, again, that exponent is an odd number. So especially if you have a polynomial function, this is a really easy way to be able to tell what kind of function you're going to be able to have. And again, it tells us about symmetry, so we want to be able to do that, okay? Now, in this example here, I'm not going to go ahead and take you through the steps of plotting these into the calculator, but what I would want to encourage you to do is go ahead and try these on your own. Remember that anywhere it says g of x or h of x or whatever, just picture that that says y equals, okay? Because remember that our calculators cannot graph something unless it says y equals. And then, of course, if you have any of these functions that use an input of something other than x, like, say, in part C it uses t, then we could just go ahead and freely pretend that that t says x and then just type x into our calculator. But every single one of these all say y equals. Again, I'm not going to take you through pulling up the calculator and graphing each one of these individually, but I will go ahead and give you the punchline. Is what you'll notice here on a couple of these, like in part A, if you were to graph that, the exponents here, these are even, or sorry, not even, goodness, these are odd numbers, right? So we have numbers like 3 and like 1. These are odd numbers, so that's kind of a dead giveaway that this is going to be an odd function. But again, that's because this is a polynomial and it happens to turn out that way every single time. If you were to graph this, you will notice that it has some rotational symmetry around the origin, so this would, of course, be an odd function. Okay, so I can leave that graphing up to you to be able to see the shape. You will see that it is symmetric on the origin. So it's going to look like that x to the third graph we just took a look at that I sketched, where it's going to look like you can rotate it around 180 degrees and it would land on itself, okay? The dead giveaway that this is going to be an even function here in this next example is you look at that exponent and it is a 2, that is an even exponent. And so again, because this is a polynomial, we might suspect that this is going to be even, of course. And if you were to graph it, you would see that this has some symmetry across the y-axis. It would be looking like I could mirror this across the y-axis and it would land on top of itself perfectly. Okay. Sometimes you would have a function that is neither. So if you take a look at the next example here, this is another polynomial function. You notice that the exponents that you have now are 2 and 1. Okay, so 2 and 1, they're not both odd and they're not both even. 2 is even while 1 is odd. And so what you might notice here is that you don't have any symmetry if you were to graph this function. So this would be neither even nor odd. And sometimes you'll have functions like that. Sometimes your functions don't have any symmetry when you go to graph them, and that would indicate that we would have a neither in that case. I'll leave those next 3 for you to do. Again, just check those symmetries, and then that's going to be it. Okay, so thank you very much for your attention in this video. If you guys have any questions whatsoever, please, as always, feel free to let me know. But that's all I have for this one. Thank you very much for your attention, and I will speak to you in the next one.